In this video, we're going to be discussing the second law of thermodynamics. So a while ago, we talked about the first law of thermodynamics, which deals with enthalpy, that the total energy content or total heat content of the universe is constant. And you often hear this phrased more casually as energy can be neither created nor destroyed. So if there is a first law of thermodynamics, there is presumably a second, which there is. So the second law of thermodynamics is related to entropy. The kind of casual phrasing of the second law of thermodynamics is often something to the effect of the universe tends towards increasing disorder or chaos. We said that sometimes entropy is described as a measurement of disorder or randomness or chaos, so this kind of goes hand in hand with that. But the idea of quantifying disorder is a little bit weird. So really, we know now that entropy is a measurement of the number of possible microstates for a system. And the better way to phrase, or the better way to think about the second law of thermodynamics is for any spontaneous process, the entropy of the universe increases. Often notated more mathematically as delta S universe is greater than 0. So in this definition, what we mean by spontaneous is that it's a process that occurs without a net input of energy. The easiest types of processes to think about here are ones that just happen naturally on their own over time, that you can't really stop it. It just kind of goes. So we should also remember here, actually circle back for a moment, spontaneous is sometimes also, this idea of a spontaneous process is sometimes also referred to as one that is thermodynamically favored. So what this is saying is for any process that can occur on its own without a need for a constant input of energy, the entropy of the universe increases. That the number of possible microstates for all of the stuff, all of the energy and matter in the universe increases whenever something just goes on its own. Entropy is really the driving force behind much of the way the world works. So we should also remember how we defined the universe in thermodynamic terms. We said that the universe is comprised of the system and its surroundings, that anything that is not part of the system, the piece of the universe that we're studying, is the surroundings, so those two things comprise the entire universe. So what this means is that the entropy change of the universe, which is what we're talking about in the second law of thermodynamics, is equal to the entropy change of the system plus the entropy change for the surroundings. So the entropy change of the system, delta S system, is the entropy change for your reaction or whatever other system you're talking about. But for us, that's typically a chemical reaction. So we learned in a previous video how you assess qualitatively whether delta S for a reaction is likely to be positive or negative based on the number of particles involved and the states of matter of those particles. We can think about how the entropy change of the system is likely to occur, whether it's likely to increase or decrease, but chemical reactions also affect the entropy of their surroundings as well, which is a little bit weird to think about. So we want to think about how that happens. How does a reaction affect the entropy of the surroundings? So if we think about a closed system, it's the easiest one to think about here, where matter cannot enter or leave the system, but energy can, is usually how we're actually working in a thermodynamic system. So the number of particles inside our system here isn't going to change, but the heat can enter and leave. And that is how a reaction actually affects the entropy of the surroundings, is through the transfer of heat. So heat is energy. We know this. And we know that chemical reactions either give off heat to the surroundings if they are exothermic, or they absorb heat from the surroundings if they are endothermic. So an exothermic reaction releases heat to the surroundings, which means that we are putting more energy in the surroundings. Which means there are now more possible microstates. For the surroundings. And more microstates means that we have increased the entropy for the surroundings. So the entropy of the reaction itself, we can figure out just based on number of particles and states of matter. The entropy for the surroundings is actually going to, or the entropy change, I should say, for the surroundings is actually going to be determined by the enthalpy of the reaction. So both enthalpy and entropy of our system play an important role in how the entropy of the universe as a whole is changing, which dictates whether or not something will be spontaneous or thermodynamically favored under different conditions. So for an endothermic reaction, everything's the opposite. Endothermic reaction absorbs heat from the surroundings. So it's taking heat away from the surroundings, means that there is now less energy in our surroundings, and therefore fewer microstates. So an endothermic reaction decreases the entropy of the surroundings.